Alright, so we're going to be covering Unit 2, Day 2 today, which covers higher order polynomial functions. So the first thing that we're going to revisit is end behavior. So to tell the end behavior of a polynomial function, we're going to write these in limit notation. And what we're going to be able to do is be able to do this without having to see the graph. But looking at the graph right now, as x approaches infinity, so when they're saying as x approaches infinity, they're talking about the right side of this graph. Well, the right side of this graph, which it is here, keeps going up forever, so it approaches positive infinity. But remember, we want to write this in limit notation, so we're going to write the limit as x approaches infinity of f of x equals infinity, because that's where we said it goes to. Okay, then we have as x approaches negative infinity, so this is talking about this left end behavior. So the left side of this graph keeps going down forever, so it's approaching negative infinity. But we want to write this in limit notation, and we're going to say the limit as x approaches negative infinity of f of x equals, and we said it equals negative infinity. Okay, so we're going to look at next is how we can tell what the end behavior is going to be without having to actually look at the graph of the polynomial. So, if you have an even degree, both sides are either going to go up or both sides are going to go down. If you have an even degree and your leading coefficient is positive, they both go up. If it's an even degree but the leading coefficient is negative, they're both going to go down. So, an example, we have 4x to the 6 minus 3x squared plus 1. So you're looking at the highest exponent. So the highest exponent here is the 6. So we're looking at this term right here. The degree or the highest exponent is even. And the number, the leading coefficient that goes with it is positive. So if it's even and positive, that means both sides are going to go up. So the graph will look something like that at the end. So then, another example, if we have negative 4x to the 8th minus 3x squared plus 1. So we're looking at the highest exponent, so this term, the first term, that happens here. And it's not always the first term, so be careful on that. So this is an even degree, but it's a negative leading coefficient. So even means they're going the same way, but because it's negative, they're both going to go down. So even means either both up or both down. Just depends on if it's positive or negative. So then if we have an odd degree, think about that means it's going to be odd shaped. So that means one side's going to go up and one side's going to go down. So depending on the leading coefficient is which way it's going to go. So for example, we have 4x to the 3rd plus 7x plus 1. So 4x to the 3rd is my highest exponent here. The degree is odd, so it's going to be odd shaped. And the number out front, the leading coefficient there is positive. So if it's positive leading coefficient with an odd degree, the first side's going to be going down, the second side's going to be going up. So I just think about that from left to right, this is going to rise. Okay, so it rises from left to right. It's positive, so it's going to go up. So then another example, let's say we have negative 4x cubed plus 7x plus 1. So negative 4x cubed is our highest exponent. So the degree there is odd, and the leading coefficient that goes with it is negative. So because it is negative and odd here, it's going to go down, so it's going to fall from left to right. So it starts out up and then it's going to go down. Okay, so odd is odd shaped. Even they go the same way. When you're working with odd, if it's positive it rises, if it's negative it's going to fall. Alright, so next we have a theorem here. So this theorem states that a polynomial function of degree n, so remember degree is the highest exponent, has at most at most n minus 1 extrema. Remember, extrema are our maximums and minimums. And at most in zeros. Zeros are where it's going to cross the x-axis. So let's just... So zeros are where it crosses the x-axis. Extrema are your max and mins. Okay, so we're going to do a couple different things with this. So first off, we're going to just tell the end behavior using limits without looking at a graph on the calculator, and then we will get out our calculator to check the extrema. So if I wanted to get the end behavior here, the only term that you care about is the highest exponent. So it's going to be this first term. That 3 is odd, and then there's really a 1 out front, so this is going to be positive. So if it's odd shaped and it's positive, that means it's going to rise from left to right. So when I go to write my end behaviors, the limit as x approaches negative infinity of f of x, so that's talking about the left side of the graph. Well, we drew that this left side of the graph is going down, so that equals negative infinity. And then if we do the right end behavior, the limit as x approaches infinity of f of x, well, that's the right end behavior we said was going up here, so that's going to positive infinity. So we were able to take this equation and get the end behavior without knowing exactly what the graph looks like. Now we're going to confirm what this graph looks like. So using your calculator, we put this into y equals. And if we graph it, so it goes something like this. So look at your end behavior. It matches what we drew here. This side's going down, this side's going up. Okay. So talking about extrema. So extrema are max and min. So you see we have 1, 2 extrema here. Well, this theorem said you can have at most n minus 1 extrema. Well, our degree was 3 here. So n minus 1 means you could have at most 2 extrema. So that's right. And then for our zeros, that's where it crosses the x-axis. So we have 1, 2, 3. So we have 3 zeros. And the theorem said you can have at most n zeros. Well, we have at most 3 zeros, and we have that there. So this graph just kind of confirms to make sure your end behaviors are correct as well. Okay, so we're going to do the same thing with part B. So in order to get our end behavior, we're going to look at the highest exponent. Remember, it doesn't have to be the first term. They don't always put it in order. If they do put it in order, it will be the first term, but they don't have to. So the highest exponent is even, and it's a leading coefficient that is positive. So even and positive means that both sides are going to go up. So when you're writing your limit in behaviors, we can do the limit as x approaches negative infinity of f of x. So the left side of my graph is going up to infinity. And then for the right end behavior, the limit as x approaches infinity of f of x equals, well, the right side of my graph is also going up to infinity. Alright, so now we're just going to confirm with the graph. So in your y equals, we'll just type this equation in. So this graph has shape similar to this. So if you look, our ends are the same. Now there's more stuff going on in the middle, but our end behavior was correct. So for our max or mins or extrema, we have 1, 2, 3. So 3 extrema. And remember, it was at most n minus 1. Well, that makes sense because our degree was 4. And then our zeros, where it crosses the x-axis, we have 4 of those zeros, which also makes sense because our highest exponent there was 4, so we had 4 zeros. Okay, so for the next one, we're going to focus on the zeros. So looking at zeros of a polynomial function. So recall that finding zeros is the same thing as finding the x-intercepts. Okay. Algebraically, that's when you set your f of x equal to 0. So this says use a grapher, so graphing calculator, to find the roots. So roots is another word for zeros, or x-intercepts, or setting it equal to 0, of this graph f of x equals, which is graphed here. So we're going to graph this in our calculator and just kind of remind ourselves of how to do this. So in your y equals, you're going to type in your y1 this equation. So you're going to put your equation into y1. In order to find these zeros, you need to put 0 into y2. So we're going to put 0 into y2. So we're going to graph. And make sure your graph looks like this graph on the notes here. So you should have 2 intersects, which we did. Okay, so what we're going to do to find these here, I'm going to write down the directions. You're going to hit second, and then you're going to hit trace, and then you're going to go down to number 5, which is intersect. Okay, so you're going to move your cursor close to one of the places where it crosses the x-axis, so close as you can get, and you're going to hit enter 3 times. So one of your answers, and we're going to round to 3 decimal places, is negative 1.083. That's one of your x-intercepts. Okay, then we're going to do it again. Second, trace, intersects. Move your cursor closer to the other one. If you don't move it, it'll keep giving you the same one. So close enough. Enter 3 times. And you should get 2.487. Okay, so let's make sure that makes sense with our graph that we have on our paper. So this is about negative 1.8, yep, negative 1, and that's around 2.5 there, which makes sense. Now something that I want to point out, we had a degree of 4 here. So by the theorem that we looked at a second ago, it said we could have at most 4 zeros, but we only have 2. The reason we only have 2 is this is saying that this f of x only has 2 real zeros, or 2 real roots. The other 2 roots, because it technically has 4, would be imaginary ones, and they're not going to show up on the graph. So once again, this is x to the 4th, okay, but it only crosses twice because it only has 2 real roots. The other ones would be imaginary. Also, just want to note, since the degree is 4 and this is a positive leading coefficient, if it's even and positive, the end behaviors would both be going up, and they do that on our graph here.